The hecklers.
Okay, good afternoon, almost good evening, ladies and gentlemen. Welcome to Breaking Ground, last presentation of the day in this room. Just a quick note before we begin, please respect the speaker. Put your cell phones and other devices in vibration mode or silent mode, whatever your preference is. The floor is yours.
All right. Thanks for skipping a little bit of bar time to come out and watch my talk. My name is Jacob Torrey. I work for AIS, and this is my talk, Cluck Cluck, on Intel's broken promises. Though I was just talking to an Intel guy who took offense to that, and so I had to put this little disclaimer that it's actually any system that supports PCI Express is vulnerable to this, virtual memory breakout. So before I put you to sleep or before you slip out to get a gin and tonic, I just want you to know that basically the crux of this talk is that the PCI Express specification allows software with sufficient privileges to break out and escape a virtual memory and then access any hardware, any memory of any process as well. I prefer this to be a discussion. This is some technical stuff, so if you have questions, please don't be afraid to jump in. If you can't hear me, just put your hand up or go like this. And then obviously any rude comments are mine only and not those of my employer. I work in Denver. Shameless plug, we're hiring. I lead the low-level systems group. So we've built a custom hypervisor for Mudge and a CFT program, which I'm talking about at Black Hat on Thursday. Built my own BIOS, C assembly, and I like the outdoors. So real quick, we're going to cover some background. There's actually quite a bit of background because it's a pretty technical CPU bug that I'm basically going to be presenting. The problem and what we're trying to accomplish, and then why it's called Cluck Cluck, and then the solution, why this happened, and then some, I think, probably the best parts of future work. So if you leave early, you're going to miss out. So really quickly, this is probably very basic for a lot of you, but virtual memory, it's kind of using paging, the page tables. Operating systems can then partition each application to have a consistent view of memory. So each application appears to have, say, in a 32-bit system, 4 gigabytes of flat memory, and there's no other programs, and that program cannot overwrite other processes or the operating system kernel. Back before paging on DOS, if you had an application that was running, it could go berserk and overwrite your kernel. So that's what virtual memory is. So it's a addressing that doesn't actually hit RAM. It's run through the processor and the memory management unit before it hits RAM. It's controlled by the MCH, which is the memory controller hub, and that kind of acts as a bridge from the CPU to all the devices on that. So the PCI, the PCI Express, the USB is all run through this memory controller hub. In the newer processors, this has all been integrated onto the die, but in previous, so pre-Nehalem, so Core 2 Duo and older, you'll actually see a separate chip and sometimes even a separate heat sink. Memory mapped I/O, that's if you want to talk to a hardware device as if it's just memory. So it will show up as a region of physical memory, and there are some defined registers there. Graphics card is a great example. They have a region of memory mapped I/O, and you just put your bitmaps there, and it will get drawn onto the screen. So it's faster, it's newer, and that's kind of the way everything is going. Before that was port I/O or programmed I/O, in which the CPU was involved in every single write of either a byte, a word, or a D word to a device. So this is a lot older. This is how you used to talk to a keyboard controller and pull and get one keystroke at a time. This is being phased out because of that. And I'll get talking about DMA a little bit later, but you can actually offload a lot of the memory mapped I/O to a separate controller so that your CPU is free to actually do work. TLB, translation look-aside buffer, really quick. It's just a CPU cache that stores virtual to physical memory translations. PAE is is a dirty hack. We can kind of skip over it, really. It's just a way that allows a 32-bit OS to pretend to access 36 bits of memory and access more. It was kind of like a stopgap measure before 64-bit OSs became popular. PCI configuration space. This is a set of registers and memory region that allows you to control your device. So if you want to tell your USB controller to eject a device, that's how you go through. You can go through PCI configuration space. PCI Express, this is probably the most important part of all these terms, came out with something called the ECAM, which is the Extended Configuration Access Mechanism. So PCI config space you used to access using port I/O, you would load into one port register the address you wanted, and then you would either read or write. So it required 2 port I/O reads, which take about a millisecond. So if you imagine how many clock cycles you're wasting on 1 millisecond. PCI ECAM is all memory mapped. So it takes all the PCI configuration space, throws it into a place in physical memory, and you can just access those registers as if you were accessing memory. CR3 registers on the CPU, it tells where the processor should go and look for the base of the page table. So when it wants to translate a virtual address to a physical address, it takes the address at the CR3, and then part of your virtual address, which is up at the top where it says PDE, that first one is kind of an index into your page directory. So that's what PDE is, page directory entry, and then an offset into here. And so each PDE, when you're using a large page, points to a 4 megabyte page. You can add in more levels of direction, so you could actually map a PDE to a page table entry. But for now, we'll just simplify this. You can get really complicated. I think with virtualization and extended page tables, you can go all the way to 7 or 9 levels of indirection. So that's why the TLB is there, to cache these very slow processes. So why is virtual memory good, and why is that considered a promise that Intel is going to break later? So it's a protective feature or promise. So the first code in, when you boot up, you can set up paging and memory however you'd like, so that your applications can't access kernel memory, your applications can't access other applications, and you can kind of go in and defend the system. Unless you have access to page tables, you can't access the page tables. So unless you know the virtual address for those page tables and that's been mapped into your process space, you can't change that for other ones. So this is the chicken and the egg problem. It's a catch-22. So unless you know how to add mappings to the page table, you can't add mappings to the page table. And it protects against a number of attacks. So if you want to access memory-mapped hardware that's not mapped into your space, so if you're a process and you don't have access to the memory-mapped I/O for the graphics card, then you can't access that and maybe do an attack on the GPU. So the goal, we want it to be able to map in arbitrary physical memory. So this requires modifying page tables, which is that chicken and the egg problem. So we need to know where they are in virtual memory. We can read the CR3 register and figure out where they are in physical memory. That doesn't help us. And so we as the attacker or good guy, we're executing as either kernel shellcode, live memory forensics. We could be a hypervisor. We have ring 0 access, so we might have found a bug in, say, the Linux kernel, but we're confined to whatever mappings Linux defines. And so we can't access those memory-mapped I/O devices, like I mentioned. And most importantly, the coolest part of this is that it's OS independent. So this is just pure x86 assembly. Windows has a mapping to the page table at a known virtual address. So it's C, 0xC, and all zeros. So if you're in this situation on a Windows system, you just go to that address and you don't have to worry about any of this. But this is an architectural flaw, so to speak. I said most of this. Oh, and you don't know where your code is executing since you can't read the page table. So that's another one. So some people have tried switching to real mode and then executing there where there's no protection, setting things up how they want and then switching back. But you don't know where you're executing. And so when you jump back out of real mode or you turn off paging, you're again going to jump to some random instruction and you're going to be in big trouble. So the crux of this problem is you need control over just 32 bits. So once you have that, you can set up a recursive mapping. It has to be at a known physical address so that you can set your CR3 there. Conveniently, PCI Express has more configuration space per device. Port I/O is slow, so they need a way to make it access faster. So this ECAM, it shadows device configuration space into a physical memory location. The base address stored in a register on the MCH. So our basic solution, we're going to construct a page directory entry that will map in the CR3 of the operating system page tables. And then we're going to mark it as present, readable, writable, and then using PS, which is the page size, we're going to make it a large page, so we don't need to have an intermediary page table entry. We then want to use port.io to insert this new page directory entry into PCI configuration space, which basically is allowing us to modify what the CPU thinks is physical memory through port.io. We can then determine the physical location of that place we just wrote to using this PCI base address, which we can access through port.io again. So the only problem seeing here is that the page directory entry has to go somewhere, and you can't just overwrite a random PCI configuration register, otherwise the system may crash. So conveniently, Intel has provided us with the Scratchpad data register. I kid you not, it says this register is for software use only, it has no functionality. So it's almost as if they were helping me out with this. So 32 bits of beautiful storage right in the memory controller hub itself, device 0, function 0, and now you can use port.io to write that physical memory in the Scratchpad register. Then you read out that PCI X bar I mentioned already, and now you know where your PD is in memory. Next step is to change your CR3 register to point to your PCI configuration space. Kernel code is marked as global in the page tables, so the TLB won't get flushed when you make that switch, and so your box won't crash, and you can still run the code. And then the CPU doesn't know anything that it's doing anything wrong, because in its view, it's just accessing memory. It has no idea what's there, what the semantics or the meaning of that memory is. And the MCH doesn't know what the CPU is using this memory for, so it thinks everything is okay. So it's kind of a disconnect in between the MCH and the CPU. Any questions about this so far? Yeah? Sure. Okay, so the operating system page table, the base, the physical address, is always stored in the CR3 register. So you can read that out, but you don't know where that's mapped into your virtual address space. And so that's what we're doing right now, is we're going to create a virtual memory pointer to point back to that CR3 register so we can access the main operating system page registers, page tables. Which one? So the Scratchpad data is where we are putting our page directory entry that points to the operating system page table. So basically what we're doing is we're treating PCI configuration space as a page table. And we got to be very careful when we access it, because there's only one entry that's valid, and there's some alignment issues where you can't have a page table pointing to an arbitrary memory address. It has to be aligned to certain boundaries. So the Scratchpad data register is a PDE, or page table entry, that is then mapping in the CR3 value of the operating system. The Scratchpad? It's just because I know that in the specification that it won't muck with any hardware. If I were to use, say, a graphics card one, it might throw crap up on the screen. So, good question. Any others? Okay. So now we have a virtual pointer to the operating system page tables, or page directory, I should say. Now we can scan these, the operating system or the real ones, for an empty entry, and then we can put a recursive page table entry that points back to the page directories that the operating system is using. So this is called recursive mapping. And then we'll save where that entry is, and then we'll have a known virtual address. We switch back CR3, and again, since we're on global pages, the TLB won't flush us, so we can continue working. And then all in a few lines of assembly, we have a virtual pointer at a known location that points to the operating system CR3. So breaking out of virtual memory, essentially. A couple caveats. So alignment, I mentioned. The CR3 register, the bottom couple bits, are more like status and configuration bits, so they get ANDed off. So you need to have some math and bitwise operations, because wherever your register is, you're going to have to figure out how that virtual address works out. You're going to need some PCI configuration registers that are okay to be trashed. There's the MCH Scratchpad register. There's a lot of other ones. If you just look through Intel specifications and just do a Control F for Scratchpad, there's some on the GPU, there's some on the SATA controller, the LPC. So there's a whole bunch of them. And so I'll talk a little bit later about extending this to say a 64-bit system where you're going to need another level of indirection, and so you're going to need multiple recursive pointers. And then the big one is this requires ring 0 and global pages. So when this talk got put up online, I got a frantic email from Intel saying, what did we do? What's wrong? What's going on? We went back and forth, and basically their argument is once you get ring 0, there's really all bets are off. And so even though there are a lot of cases in which if you find the little exploit, you getting this was a kind of a pivot point to insert yourself. So we're actually going to get rid of that restriction to be in ring 0, and we're going to move on from that. But go on from there. So any questions? Good? Okay. All right, so how did this happen? Kind of a classic feature creep example. So Intel made some kind of assertions back in the day when they brought out their virtual memory and their paging protections. And then down the road, they said, okay, well, now we have these PCI Express buses that are moving data extremely fast and have huge amounts of configuration. This is too slow doing it all over port I/O, so let's throw this in. And then they violated those assumptions without going back and verifying it. This has happened before. There's the SMM caching bug, which is where they added a new feature without realizing that it, forked everything up. There's some virtual machine side channels where they went for the performance over security decision, etc. So, as I said, Intel reached out, spoke with Branko Rodrigo, who's actually in the other room right now. He's also speaking at Black Hat, so try to bump into him if you see him. His thoughts, basically, this is an impressive attack in the sense that it makes something OS independent. So really, there's no point if you know what your target system operating system is, because either the Linux kernel is identity mapped, or Windows, it's at a known virtual address. This is just a cool flaw in the x86 architecture. And so if you already have ring 0, you're already pwned. So not really a big deal, but they're going to go and provide some education to the OS developers so they realize what can happen when you have these flaws. And it's already possible for target operating systems. So cluck is not target specific. If you know you're hitting an x86 system, regardless of what operating system it's running, this x86 assembly will run and work. If you're trying to target, say, a Windows 7 machine, then you would just use the target-specific attack. So this is more of a cute, weird machine or an Easter egg rather than a 0-day. Hopefully that's not a letdown for some of you. So if you're out and building a new system, these are some suggestions I would provide to make sure that you don't have a similar issue. So codify your verification. Formalize what your platform is guaranteeing and what it does and what it doesn't do. If you're taking input, formally parse that, and so that way you can reject bad input rather than going into some unknown state. So that's kind of the example behind ROP, where you don't formally parse that input, and that input is return addresses, which is essentially an assembly language for a ad hoc virtual machine. So you need to codify what your platform or what your design is doing, and then what its guarantees are making, and what assumptions you're making that, for example, the adversary can't do X, Y, and Z. And then when you add a new feature, go back and review everything. So, one thing I think, Alloy is a tool by MIT to do model verification. So you can write, in a couple hundred lines of code, you can write a formal model for an architecture, and it can check a whole bunch of different cases that you wouldn't be able to check. So before you start writing a single line of, C code or Python, you can make sure that your design is sound and there's no invariance that can be broken. And then you just update this model and run it again whenever there's a new feature that you add. And obviously maintain an adversarial mindset. So this is probably the perfect audience. You guys already have an adversarial mindset. But if you're building a system, don't forget that. Don't think, okay, I'm just going to worry about my class diagram. Think about how you would attack the software you're building. And then are those assumptions, a reliable or a safe bet when you're thinking about your adversary. A couple of use cases. This came up originally as a forensics. So you can plug a PCI device in. So actually there's an NSA playset talk at DEF CON about exfiltrating data over PCI. So they're doing it at the PCI bus mastering level. This is if you can plug something in and get software to run. So you don't know or you can't trust the OS API. So you can't just execute code in kernel space and say, okay, Windows, mmap.io space my PCI device, because you're not trusting and you don't want to alert the operating system that you're doing some kind of forensics. You need full memory access, as you want to get the whole dump, and then you're going to need memory mapped.io to whatever device you're exfiltrating. So if you want to get direct access to the NIC, and then that way you can send your data off over the network without, using the operating system APIs, which might get picked up by some kind of host-based protection. So that's where you can use this. It's basically a memory query attack where you're directly accessing it rather than going through OS APIs. Hypervisors, it provides a memory or an OS independent way to map in memory. So if you're writing a thin hypervisor, you want to do some introspection, and you don't really want to care about how whichever operating system you're virtualizing. So something like Blue Pill is a rootkit example. They'd be able to go in here and use this to map in memory regardless of whatever operating system they're subverting. And then the last, kernel shellcode for whatever reason you might have. And you want to be able to pivot from a little blob of shellcode, x86, that doesn't call any specific kernel functions, to full system memory access and memory mapped I/O. Once you have that, you can inject yourself anywhere. You can get a lot of rootkit persistence. You can hook the IVT or the IDT, and you can really, completely hone the system. All right. Any questions before I go to? Okay, cool. Future work. So these are all theoretically possible. I just haven't written them up yet. So you can extend this to work on PAE or 64-bit. You're just going to need to find larger Scratchpad registers or more of them that will point. So you'll have to have a page directory entry that maps to a page table entry, which is also in PCI config space, and then maps to memory. So it's more of an engineering task. It would be really nice if you could remove your global page requirements so that you could execute anywhere as long as you had kernel privileges. And then remove ring 0 requirement. This is the big one. So this actually happened when I was emailing with Intel, and they said, this attack is not really that impressive. So I went back and said, okay, well, now I've removed the ring 0 requirement. So an application running in user space with I/O privileges, such as X server, which is run on a number of systems, or if you're running in BSD with secure level, you can actually have full memory access from ring 3. So don't tell me my attack is pointless is the outcome of this. So this hasn't been implemented and tested, so it's future work, but in theory everything should come together. A little bit more background, and then our goal is basically to get from ring 3, so user space application with an I/O privilege to talk over port I/O, to ring 0 or arbitrary physical memory access. So why would you care about this? You need root to get IOPL. So on BSD systems with secure level, you can get root, but root doesn't have access to kernel. You can't load a kernel module in a BSD system on secure level. So this is a way to break out of that and get into the kernel. And then it's also kind of a neat trick. So really quick, the overview for the technical ones amongst us. We're going to use DMA. This is actually a DMA attack to overwrite either kernel code or the IVT. We're going to set up a table in the ECAM pointing to target memory addresses we want to overwrite. We're going to write a payload to disk, and then we're going to use port I/O to tell the DMA controller to read from that block, or have it read from memory first so we can do a patch and then write back. And so this essentially allows us to do access to arbitrary physical memory. So a little bit more background. So DMA requires a few things. So the reason you can't do this without this trick is that DMA requires both a buffer, or it's a PRDT, physical region descriptor table, which has to be stored at a known physical location. to tell the DMA controller which blocks and where they need to go, and then also you need port I/O. And so up until now, there was no way to write this PRDT at a known physical location. So even if you had exploited X server, you couldn't do this DMA attack. So basically, it needs to be at a known physical address if only there was a way to write physical memory using port I/O at a known location. So conveniently, I just showed you that. So you can set this table up and you can store your target memory address. So I would recommend reading out the IDTR, which is the pointer to the interrupt descriptor table, and then maybe modifying that. So then DMA, this is the old school DMA. So this is ATA DMA. Then you can use port I/O to tell the DMA controller to read and write. You got to give it kind of, if it's a read or a write, start and stop. You don't care about the status byte. And then a pointer to the table we already set up. And then you use port I/O to communicate with the ATA controller. And then you can communicate over the standard ATA or a TAPI spec. You could also use a CD drive, but I don't know how many CD drives have shellcode on them, but you could if you wanted to. And then there's the different read DMA and write DMA bits. So you now theoretically have full read and write access to the entire memory space. What you do with that is left as an exercise to the reader. So some caveats as well. Newer drives, mostly the SSDs, are in what's known as AHCI mode, which is something you can set in the BIOS. And they won't respond to these ATA commands. And so this won't work in AHCI mode. And then Intel VTD, which is their extensions for hypervisors that provide directed I/O capabilities, which prevent a DMA attack against a hypervisor. This will allow you to do that if you had an operating system with this capability. As far as I know, that's not happening right now. All right, so I'm going to let you out early so you can get drinking, but a couple conclusions. As I said, it's not really a security hole in itself because you already need to have some privileges. It's a nifty trick for sure, and x86 is full of weirdness. So there was Sergey brought us up front in the audience, and one of his students showed that the memory management unit in an x86 processor by itself is Turing complete. So you can simulate any Turing machine by setting up your page tables and never actually executing an instruction. So basically this is such a complicated architecture that there's a whole bunch of weird things you can find. A new architectural feature creates a broken invariant from the past. Intel's pretty cool. I hope they can take some jabs. And then you'll be able to read more in the latest POC GTFO, which is coming to a printer near you. Or on Friday, you can grab it from the No Starch Press booth at DEF CON. With that, any questions? Perfect. Just the response I was expecting.
Oh, one question.
So can you go back to the solution slides and comment on which invariant they broke?
Sure.
I mean, what were they thinking they were preserving?
Yeah, so I would say that the promise they broke is that currently the way that when you bootstrap a system, you start off in real mode, which is completely unprotected. Any software that runs in real mode has full power over the system. And so an operating system immediately bootstraps itself to protected mode. And then it can set everything up where applications can't access kernel memory, can't access this device or that device. And so that invariant of basically whoever's the first in, who's ever the king of the hill, can then defend everyone else, that invariant has been broken now. So now if you come up, this is basically a catapult that allows you to smash your way into the castle and take over and kick the operating system out if you wanted to. You could then create a little region of memory where the operating system can't even read it. So even if there was some kind of active operating system defense, it wouldn't be able to read the region of memory you're hiding yourself in. Does that answer your question? Okay.
So you have this PCI configuration area where you put the table, which is great. This is lovely. I wish I thought of that. So at what point does that get inserted into the say the boot process?
This can happen at any time. I can actually show you. Oops, let's see here. My code is a Windows kernel module that you could load at any time. So this can happen after the operating system has completely set up its defenses, and it is assuming that even if you were to get access to ring 0 from some kind of driver exploit, that you wouldn't be able to kind of pivot from that. And so this brings it back so that your attack can then access anything as if it was in there first.
So the invariant seems to be, right, that they took their the knowledge of the location of the page table as a sort of a capability.
Exactly. Yep.
Right. And so as you were, as you mentioned that they said that, well, you already have if you already have ring 0, well, sort of the capability model.
Yes.
Is based on you need to know this magic number.
Exactly. Yep.
Even though you can write all over memory, but you need to know this magic number to do so purposefully.
Yes, and so I think there's two. There's that, which is probably the crux of it, and then there's the other one is that up until now there's been no way to write to physical memory at a known location, and so virtual memory was this perfect, unescapable jail that you could have. You could have 4 gigabytes of memory in your application, but only have 2 gigabytes of memory. You're not sure where that memory is going. It's just it's off and it's managed by the operating system, and so that prevented you from doing a lot of stuff. And talking to hardware, because hardware usually has both port I/O and a memory mapped I/O component, so that the memory mapped I/O component was kind of a protection, the capability that unless you had access and you had that mapped into your address space, it was essentially hidden from you.
Yeah, it's interesting how much. I mean, what other leaks you might be able to find with this?
Yeah, so my weekend projects have been trying to get rid of the ring or the I/O privilege requirements. So that would be a fully generic privilege escalation on any operating system. So that's hopefully what I'll be talking about if I can have some results in the next year or so. All right.
Any other questions? Okay.
Cool.
Thank you very much.
Thank you.
This is end of line for Breaking Ground tonight.